Hi everyone, welcome back to Project 2845. Today we're talking about our second gain stage and the driver requirements for our parallel 845 tubes. When I introduced the project, I think I showed this exact same page, and this was the describing or documenting at least the voltage swing requirements for our 845 grids in order to maximize the output power for our target operating point. And if you recall, we needed a minimum of 164 volts peak, which is equivalent to 116 volts RMS input swing on the grids of our 845s. We also need a driver that can drive the Miller capacitance. So with our two 845s, the Miller capacitance is going to be approximately 180 picofarads, plus whatever capacitance of additional wiring between the driver and the 845s. That capacitance and our large voltage swing requirement imposes a slew rate requirement that must be met in order to not have slew limiting distortion. And so, again, we talked about this, but just documenting it here again, the slew rate at increasing frequency becomes fairly substantial, or the slew rate where you need from a driver. And from there, we can start to figure out what the current requirements are just to meet the minimum slew rate. We discussed previously our first gain stage, which is the 6SN7 mu follower. Here I printed out the THD versus output profile we captured and documented before. I'm planning to use this stage somewhere between 10 and 20 volt RMS output, and that will keep us far away from this clipping region. And with this output voltage, we can now figure out what sort of gain our driver needs to meet the voltage swing requirements from our driver to our 845 tube grids. So there's a second gain stage and potentially driver that we're going to implement between our 6SN7 mu follower and the 845s. If I assume from our mu follower stage that we will use 10 volt RMS output, that's 14.14 volts peak. And in order to hit 170 volts peak, we need a gain of roughly 12. If we take or allow for a 20 volt swing output on our mu follower, we get 28.28 volts peak, or a gain of 6 to hit our 170 volt output swing for our 845 grids. So basically, if we can allow a range of either 10 to 20 volts RMS, a 6 dB swing or range that we want to get from our output swing of our mu follower, our gain range for our second driver stage is somewhere between a gain of 12 on the high end and a gain of 6 on the low end. So the idea I had for a combination of a second gain stage and a driver for our 845s was to use a 6BX7. The 6BX7 is an octal twin triode, which is really like a miniature power tube, and we'll take a quick look at the data sheet in a minute. I was thinking of basically having AC coupling our 6SN7 mu follower into the input on one half of the 6BX7 triode for a common gain stage that's constant current source loaded at approximately 15 milliamps. This constant current source will maximize the gain of this tube, and the mu of the 6BX7 is 10, so that falls right into our range of gains that are acceptable in order to from our 6SN7 mu follower to get the voltage swing on the 845s. And the reason I also want to use a constant current source is not only will it give us the mu of the tube of 10, but it'll linearize this stage and hopefully give us very good linearity, because we need basically as much signal swing out of this tube as we can get. The other half of the 6BX7 can be configured as a cathode follower, again using a constant current source and then driving our 845s. So the 6BX7 kind of fits both bills. It's got a gain where we need it at 10, but it also is very robust. It's got a high transconductance and therefore should have low output impedance, and I approximated of 132 ohms to our 845s. On top of that, it also can handle high currents. So I'm thinking of potentially running this cathode follower at 30 milliamps in order to meet our slew rate requirements, as well as potentially drive a little bit of grid current into the 845s on transients. So this should work pretty well, or at least in theory it should work, until we take a look at the datasheet. Now, unfortunately, the heater to cathode voltage on a 6BX7, heater negative with respect to cathode, is 200 volts. Now, unfortunately, our cathode follower, in order to maximize signal swing, if we assume we're going to be sitting close to half of our supply, I estimated maybe 290 volts on the cathode, DC voltage on the cathode at idle. So that means we need to elevate the heater for this cathode follower by greater than 200 volts in order to meet that heater to cathode requirement. However, since this tube shares a heater between sections, this is a grounded cathode amplifier. The voltage across, or the voltage on the cathode here, is just the bias voltage, so that would be 20, 30 volts, maybe something like that. So if we elevate the heater for this tube to meet the heater to cathode voltage, we'll violate it on this tube, and vice versa. So unfortunately, using a single triode based on the voltage, the voltages we need, and to maximize our swing, we can't use the same tube with the same heater for both a gain stage and a cathode follower. One of these stages will be grossly violated from the datasheet maximum or minimum heater to cathode voltage. Before we move on to our proposed solution for the heater to cathode problem between the gain stage and our cathode follower driver stage, I wanted to show a little bit more information on the 6BX7 tube and why it's such a good driver, as well as some proposals on why I wanted to use it loaded with a constant current source for both the gain stage and driver. But first, the curves of the 6BX7 are pretty impressive. It's really a miniature power tube. It can handle quite wide current swings and quite wide voltage swings. And in fact, in the data sheet, the maximum DC, so our static plate voltage, can be up to 500 volts, and actually can withstand even a peak pulsed plate voltage of 2000 volts. So it's a very robust tube. And this is typical of these tubes actually designed for vertical deflection of CRT or old televisions, essentially. They need to be very linear and have really robust current and voltage swing capabilities. It can also handle a static or average cathode current of 60 milliamps. Now we wouldn't use this tube at that extreme level, but based on its data sheet and the curves, you can see it's a miniature power tube. The reason I wanted a constant current load both the gain stage and the driver stage is to essentially maximize headroom, as well as handle driving low impedance loads much better. So with a constant current source, and I'll mention the 6SN7 mu follower behaves very similarly, except we're using, if you remember, a tube on top to essentially act as a constant current source. Here, if we assume we've got a pure constant current source on the plate, or applying the plate load of this tube, we get essentially a horizontal line at our desired cathode current. So for example, if I set it up for 15 milliamps, the tube is going to be essentially sweeping along this vertical line, assuming no load is connected to the output of the tube. I estimated if I'm using depletion mode MOSFETs for my constant current source, I've got about 20, if I use a 500 volt supply, I've got about a 20 volt margin I need to leave on the constant current source in order to keep the current regulated. So this region here we can't operate in because we need to maintain approximately 20 volts across the current source for operation. But so basically, if we've got this horizontal line, if we compare this to, say, resistive loading this stage with a 500 volt supply, and if we wanted to keep the same DC operating point, I show here that we would need approximately this line here, a 15 k ohm plate load. So a 15k ohm plate load with a 500 volt supply will get us roughly the same operating point as a 15 milliamp constant current source, as it's the central node here. But what you notice is just by, if I used a plate load resistor rather than a constant current source, just by setting up that, or just by adding that resistor, the load line has already rotated like this. So say, for example, then I've used a 15k ohm resistor on the plate, say, on the plate of this tube to set up its operating point. Any additional load that this tube sees that's AC coupled or even DC coupled is going to continue to rotate this load line. So for example, if I had a 15k ohm load and then drove an additional 15k ohm load, the load line would continue to rotate. And that's shown here on line number 3. This 7.5k ohm load is the parallel combination of essentially two 15k ohm loads. So we basically are losing headroom in this stage as soon as we load this stage with anything, I guess any load other than our load resistor we use to set up our operating point. In complete contrast to that, if we used a constant current source, our normal operating is completely horizontal like this. That means then if I drive an external 15k ohm load, our load line would rotate to this. So if it was resistive loaded, this load line would be our operating point. If it's constant current source loaded and we drive 15k ohm load, we can actually drive this load. This is really desirable because as we drive lower and lower impedance loads, and especially with like a cathode follower driver stage, this load line will continue to rotate as we drive reactive loads and more difficult loads. And so we're going to run out of headroom and drive, we're not going to get our 500 volt or 480 volt swing. We're going to continue to rotate this load line around our operating point as we drive harder or more difficult lower impedance loads, and we'll start to sacrifice headroom. So I guess what I'm getting at is this constant current source is extremely useful because it gives us margin to drive quite heavy loads until we start running out of headroom. So in this case, as I mentioned before, if we used 15 milliamps with a constant current source load, we can drive externally a 15 kilo ohm load before we even start to give up any headroom. That is not the case as if we set up this operating with a 15k ohm plate load resistor and then drove an external 15k ohm load. I hope that makes sense. I guess the one other thing I'll touch on here is, as you can see, if I continue, if I increased my operating current through the stage and essentially slid my operating line up, we can handle even more and more rotation before we run out of headroom. So that's why constant current sources, especially with the voltage swings we need, are very nice for both the next gain stage and the cathode follower output stage. Both are very tolerant or gives us good tolerance to varying loading conditions. And that's, again, especially true with the cathode follower driving our 845s, where the load's going to be fairly capacitive, and potentially at peaks, the 845s are going to draw grid current, which is going to make the load impedance seen by our cathode follower essentially collapse rather quickly. So again, we've got quite a bit of tolerance before we start driving the tube into cutoff due to our AC load line. Now that we talked a bit about constant current sources and why they're useful for both the plate load of our second gain stage and the cathode load of our cathode follower, I wanted to discuss our solution to the heater to cathode elevation problem I discussed earlier. And really the solution is none other than we need to split up the function between two different tubes. So what I'm thinking is using a 6AH4 GT for our second gain stage and continuing to use the 6BX7 as our cathode follower. The 6AH4 is very similar in specification to the 6BX7. It has a static plate voltage handling of 500 volts, a peak plate voltage of 2000 volts, plate dissipation of 7.5 watts. So again, it's looking like this is very much similar to the 6BX7 in that it's a miniature power triode, and a average or static plate current of 60 milliamps. So it's a pretty hefty tube. The only real difference between these is that the amplification factor of a 6AH4 is slightly less. And it's basically a mu of 8, where if you recall the 6BX7 was a mu of 10. So slightly less gain, and we should get close to this 8 if we constant current source load this tube, which is still well within our range of what we were targeting with our 6SN7 mu follower output of either 10 volts RMS or 20 volts RMS. This gain of 8 should still give us enough gain to get our voltage swing requirements we need. For the 6BX7 GT, actually this might help us out a little bit in driving the 845s, rather than using one section as the gain stage and one section as the cathode follower. Since my gain stage will be taken care of with that other 6AH4 tube, what I'll do is I'll wire both sections in parallel, and we'll double the transconductance and have our output impedance, and also actually double our current handling capability of this tube. So it'll make this an even more robust driver for our 845s, and I think it's going to work extremely well once we set up our operating point and get enough current to meet our slew rate requirements, and even have even more current on hand to potentially drive grid current into the 845s. This should work really nicely. Before we close out this video, I wanted to discuss my plan for the constant current sources for the second gate stage and the cathode follower. I'm planning to use these depletion mode MOSFETs from IXYS, and these are 1000 volt, 100 milliamp capable depletion mode, N-channel depletion mode MOSFETs. And what a depletion mode MOSFET is compared to an enhancement mode MOSFET is that they require a negative gate voltage to drive the device to full cutoff. So it's very similar to either a JFET or a vacuum tube in the sense that to stop current flow, the gate actually has to be negative relative to the source. And just like a vacuum tube, that's actually really easy to achieve by adding a source resistor and referencing the gate back to that. Just like we've got a cathode resistor in a vacuum tube, we can develop a voltage drop across a source resistor, reference that back to the gate to bias our conduction through the device. So that's really handy, and it turns essentially a 3-terminal device into a 2-terminal constant current source without the need for other external circuitry to supply our reference for the gate. Here's how I'm actually going to implement this. I'm actually going to use each constant current source is going to have 2 of these 1000 volt depletion mode MOSFETs in a cascoded configuration. And essentially that cascode just improves the impedance characteristics of this constant current source. Each FET will have 1 k ohm resistors on the gates, just like a grid stopper resistor on our tube stages. These will help DQ any inductance or capacitance in our wiring and prevent these from oscillating. And then at the bottom of the stack, I'm planning to have a set amount of fixed resistance and then a set amount of adjustable resistance with a trim potentiometer to adjust our voltage drop for our given current across the stack, which is again referenced back to the gate. So by adjusting this lower resistor, we adjust the resistance and therefore can adjust the current through the stack. So, like I said before, we've turned these 3-terminal devices into a 2-terminal constant current source, or in fact actually a sink. So this same setup can be used at on the low side of our cathode follower and provide our active load for our cathode follower. So this can be used in either high side or low side configurations without any additional components. And that's really convenient, and why depletion mode MOSFETs are a great way to build constant current sources. I've been running some simulations using this LT Spice program. I was able to find models for these MOSFETs in LT Spice, so you can see them here. And what I've been doing is using this floating AC source to inject an AC test signal and then measure the current. And by taking the ratio of the voltage and the current, I can get the impedance, or at least the modeled impedance that LT Spice is going to give me for this constant current source for its frequency. And if you remember, we want a really high impedance for a nice horizontal load line on our tube stages. At least according to LT Spice, it's suggesting that at low frequencies at DC, at 15 to 20 milliamps of current, we should get about 63 mega ohms of impedance. So this is going to act like a 63 mega ohm resistor on the plate of our gain stage or on the cathode of our cathode follower, while forcing our fixed current. And again, that's going to give us our nice horizontal load line we're looking for. At increasing frequency, the gate to source and gate to drain capacitance eventually shunt the effective impedances of the nodes on the MOSFET, and eventually we're going to have a decreasing impedance. According to our simulations, we're still at 10 mega ohms though at 20 kilohertz, and even at 100 kilohertz we're at 1.3 mega ohms. So across our entire audio band, although the impedance looks like it's changing quite dramatically relative to what a normal plate or a cathode resistor would look like for setting up our operating point, this is a massive impedance, and again will linearize our tube and give us that nice flat load line. So that, I think, closes this out, and I hope everybody enjoyed this and found this interesting, and we'll talk with you soon. Thanks for watching.